Hey, it's Mr. K doing a video for AP Physics 2. This is going to be a fluids mechanics video. Topic is going to be on Pascal's principle or Pascal's law. And Pascal's law just says that a change in pressure at any one spot in an incompressible fluid is going to be transmitted throughout that fluid. So if I have a small change in pressure in one spot, it should equal a small change in pressure in all the other spots. So like if you have this kind of U setup here, let's say these are open-ended. If we put some water in one side, that water should go down and go up on the other side and try to even itself out. And as we added more water to the left side, the water on the right side should feel that equal amount of pressure to want to go up and even itself out, balance itself out. And so with this setup, what they usually would say is, hey, let's go ahead and fill this thing with water, let's say to this level. And so you should have this level of water as well. But maybe we also fill it on top of that with a different fluid. Maybe some oil or some just heavy, maybe oil. So let's say we fill this thing with water, we fill it with oil up here, and when we fill this thing with water and oil, because oil is less dense than water, it should want to float on top of it. But then on the other side, you would have some water level here. Okay, and we would expect this water level to be not as high as the oil on the left side because water is more dense than this oil. And so just kind of throw it back to cooking. If you have oil and you put it into some water, that oil is going to float to the surface. So that's essentially what's happening here. So this is going to be oil. This is going to be water. And we got to figure out what this difference in height is. And so to look at this, we're going to consider the pressure on the left side and pressure on the right side, and the pressure on the left side should equal the pressure on the right side, especially down at this level. So the amount of push down on the left side should equal the amount of push down on the right side. We're going to also talk about the atmospheric pressure that's trying to push in on the left side and right side, and those two are going to definitely cancel out, but it's worth mentioning because we would want to talk about absolute pressure or talk about gauge pressure. And so the absolute pressure would be the pressure of the atmosphere plus the oil plus the bit of water that's on the left side. And on the right side, it would be the atmospheric pressure plus this level of water on the right side. Well, the gauge pressure would be just due to the stuff that's in the system here, the oil and the water. So let's say that we have oil of density, let's say 900 kilograms per meter cubed, and the water is going to be of density 1,000 kilograms per meter cubed. And we pour in some water on the left side, and let's talk about the amount of oil that we pour in. Let's say we pour in, like 20 centimeters of it, so 0.2 meters worth. And the question now is, how much difference in level is the left side to the right side? So just to compare, the pressure on the left side should be equal to the pressure on the right side. Okay, and so let's try to develop an equation, and we'll see some things cancel out definitely, but let's go ahead and develop an equation. So on the left side, we're going to say, all right, we have an area to this tube. It's going to be the same as the area on the other tube, just for simplicity. And on the left side, we're going to take the density, and the density of the oil is going to be multiplied by the volume of the oil. So the volume of the oil would be the area of the pipe times this H, that's right here. And then we're also going to say, let's call that an H1. And then you have to have the H of the entire thing, which is going to be, I should have done this a little bit bigger, over here to the bottom, right, to this level over here, because this bottom part is definitely going to cancel out. And let's just call that an H. Well, let's call that an H, just H, all right? And so this will be H2, and this is going to be some H3, okay? So what we know on the left side is that H1 and H2 equals H, and so we have the density times the volume, and that's going to give us the mass, and we're going to say that mass is going to be multiplied by some G, all right? And I did say pressure, so really pressure is rho g h. So in fact, I don't really even need to worry about this A, and we're gonna see exactly how that happens here, I think. Also on the left side, we're gonna add in some pressure due to the water. So water is gonna be H2O, and we have the area, and we're gonna have H2 for that. And that should equal the pressure on the right side, which is going to be, again, the water times that area times that H3. And as you can see, that area is the same right here, right here, right there. So this does end up becoming pressure with just the rho GH. Forgot to put the G in because I am getting distracted by my dog. There's PB. And anyways, the A's are going to cancel out. So we have rho of oil. We have the height 1 of oil times G. Actually, all the G's cancel out too, don't they? So not only do the areas cancel out, making this just pressure, but all the G's cancel out too. So, choking. All right, rho, H, A's, G's are all gone, plus rho, H2, and that's going to be equal to rho and H3. So, if we were to designate an H2, and let's make H2 a value of 0.2 meters as well, then what we were going to see is that we can actually solve and say H1 and H2 should be equal to should be able to solve this equation to find H3. So oil, said it was 900 here, H1, 0.2, it could be different, but we chose 0.2, plus water, 1000, H2 again, 0.2, is equal to water, 1000, H3. Do a little bit of math, divide the left side by 1000, divide the left side by 1000, we're going to get that gone, and this is going to be 0.9, and so in the end, we just get 0.9 times 0.2 plus 0.2, and that's going to be 0.38. So, H3 on the right side is 0.38, and kind of like on the picture that I drew, this height 3 is going to be slightly less than the total height on the left side. And so Pascal's principle says any change in the pressure on one part of the incompressible fluid is going to change the pressure everywhere else. That's why this thing, as we add oil in, would want the water to rise on the right side. Alright, little flip in the video because I ran out of room. I just decided to do an entirely new video. So another example of that is going to be the pump jack, where we have the piston on the left side and piston on the right side. They're connected by some incompressible fluid down here. And what, again, Pascal's principle says, hey, is that any small change in pressure on one part of that incompressible fluid is going to equal a change in the pressure everywhere else in that incompressible fluid. So if we were to take this piston and push down on it, this piston should go up. So this piston on the left side has an area 1, piston on the right side has an area 2, because we're going to consider volume change first, and then we'll start talking about work and talking about forces. But just looking at this, if we were to push piston 1 down a height h, and what that should be is some change in volume here. That change in volume should be equal to the change in volume on the right side. So this part going down some volume, this part should go up some volume. And if we look at the volume on the left compared to the volume on the right is much, much, much greater in this area here. This area is much, much, much bigger. And so if I had a change in volume here, that would result in a much, much less change in height here on the right side. So we're going to look at how much this right side should go up based upon how much the left side does go down. And what we need for that is the areas and how they're related. So the way that I kind of drew this was that the area on the left side, that cross section, that length across is about 1 centimeter. And then here on the right side, I've got about, it looks like about 1.5 centimeters. So we go from a radius on the left side of about 0.05 of a centimeter. And on the right side, we go to a radius of about, let's be a little more exact about that. I've got 2.7. So I've got 2.7 over 2. 2.7 over 2 is going to be 1.35. And that's going to be that'll work. Centimeters. This will be fine. So if we talked about the area on the left side compared to the area on the right side, the difference in the radius is going to be 1.35 divided by 0.5, and that's going to be about 2.7. So my radius on the right side compared to my left is going to be radius on the left is equal to the radius on the right if I multiplied the radius on the left by 2.7. Okay? Now what that does for our area here is that our areas, remember the area of this shape anyway, is going to be pi r squared, And so if we were to put in an area that is 2.7 times, or the radius that is 2.7 times, that is not equal to a radius change. Hold on. That is not equal to an area change of 2.7. That is equal to a area change of 2.7 squared. So if we were to put in this radius of 2.7 times the original, it's not 2.7 times the area, it's going to be squared that. So what is this? 7.29. So area 2 should be equal to area 1 if we multiplied area 1 by 7.29. Okay, so that's going to be what we're going to use here. Just to look at it, let's consider our pressure and our volumes. So the volume on the left side, if we changed it by this amount, my change in volume on the left side is equal to the area 1 on the left side times that height. And that should equal the change in volume on the right side, which would be equal to area 2 times its respective height, h2. And so if we know the relation now that A2 is actually 7.29 times that of A1, then we can say, all right, A1, H1 is equal to 7.29 times that of itself, A1, and that'll be some H2 on the other side. So as we see, if we have 7.29 right there, then H2 must be 7.29 times smaller than H1, giving us a much lesser change in height on the right side compared to the left. So A's cancel out. H1 divided by 7.29 will be equal to H2, just to prove it. And if we said, all right, maybe we say H1 is going to be 0.2 meters right here, or 20 centimeters, then our H2 on the right side should be much less than that. What is 0.2 divided by 7.29? It's going to be 0.0274. So very small. The H over here is 0.0274 centimeters, and that's going to be H2. It's going to be very tiny. It's even tinier than what I drew. So how does that really help us? So we look at energy, we look at forces. We know that the pressure on the left side should be equal to the pressure on the right side. And so let's just run a little example. If I apply a force to the left side, that would be equal to another force on the right side. That would go the other way. So if I were to talk about this as far as maybe 200 newtons of force that we're pushing down on the left side, what's going to happen to the right side? And so let's look at that. So the pressure on the left side, P1, is equal to that force, that 200 over the area, A1. And that should equal out with the pressure on the right side, P2, which is going to be equal to some force. But again, that area is 7.29 times bigger, so 7.29 times bigger than A1. And so, again, what does that do for us? That actually increases this force. So 200 times 7.29, that's going to be equal to 1,458. So the force on the right side is 1,458 divided by, again, that's 7.29 A1, so that the pressure is still the same. But look at what happened with the force. It's huge, right? So I can use this to press down on the left side, and the right side is going to have that amplified force at the cost of the distance. You know, one last way to look at this is this force is applying itself over a distance. So the work done is that force for that distance, or the force for that change of y. And so the work done on the left side better equal to the work done on the right side, because conservation of energy is a thing, right? You can't just create work from nothing. So the work on the left side is going to be that 200 at that distance of 0.2. Well, that's going to equal some amount of force on the right side at that distance of, what was it, 0.0274. So look, again, 200 times 0.2 divided by 0.00274 gives me that huge force once again of like 1458 or 1459. Okay, don't worry about that being off by 1 Newton. That's just rounding. So Pascal's principle, again, one small change in force or area or pressure on one part of an incompressible fluid is equal to another change everywhere else in that fluid. And it's very useful for just moving stuff. That's how a lot of our mechanical things work nowadays, is hydraulics, especially if you want to amplify that force. All right.